All right, if you'd like to join us here in about 1 minute, we're starting the last presentation here in the Exhibitor Forum. Last presentation starting in 1 minute with IBM. Thank you.
Some more, you had me in pieces. I was ready to leave this. You took my hand from best to stand by my side. You got me high. Oh, the night with you is never long enough. Hold me in this moment. Love will see us through. You got me, you got me, you got me higher, higher every day. You got me high.
People get seated. Okay, welcome everybody. I'm Derren Dunn. I'm from IBM Research, the T.J. Watson Research Center. And today I'm going to be talking to you about EDA as a solution, enabling world-class dynamic design and foundry-facing workflows in the IBM cloud. So to start off with the definition, what is our EDA as a solution? It's a value-add solution built on top of our HPC cloud offering to enable world-class hybrid cloud infrastructure for EDA design workloads and also cloud-only infrastructure. The components that we offer that are value add are to be able to treat infrastructure as code. We have a way that I'll describe in a few minutes to bring together some key advantages that IBM has in our product portfolio to generate unique infrastructure. Our infrastructure as a code consists of Terraform, Ansible, kernel parameter settings, service parameter settings, custom vendor configurations, as well as research-developed design flows incorporating AI and ML. What you can see in the upper right-hand side of this diagram is a level diagram of how we built everything from the client data center through on-prem infrastructure, cloud infrastructure, the levels that we're going to talk about in a little bit, particularly LSF, spectrum scale storage, Aspera, and high-level security for secure data protection chambers. On top of this, we're able to configure vendor tools from the main vendors as well as user interfaces and APIs. So if you think about the picture in the lower right-hand corner, most people have multiple types of on-prem infrastructure. They have research infrastructure for testing and developing new technology nodes. They may have a development infrastructure for actually doing design, and a production infrastructure for different types of workloads and finishing designs. If you think about this for a minute, this is an awful lot to handle for any IT team. But if you're thinking about hybrid cloud burst or using cloud-only infrastructure for specific projects, what you really want to be able to do is recreate or make as seamless as possible the infrastructure you have in the cloud as a connection to your infrastructure on-prem. And that's exactly what our offering does. We're seeking to make it as simple to submit a job to our public cloud infrastructure in the IBM cloud as it is to submit to a separate LSF queue. So what are the key components that we bring together with IBM as a service? And if you think about hybrid cloud burst, it's not too difficult to configure compute in the cloud for HPC. What's more difficult is how do I get the data that I really need from on-prem into the cloud and not just copy everything. If you were to talk to me or any other designer and ask me, what are the files you absolutely need to have in the cloud? I could probably be right about 90% of the time. And the reason for that is we all build up legacy infrastructure or infrastructure that depends on previous development. So what you want to be able to do is develop data hydration strategies that enable you to only pull what you want into the cloud and then do your runs. And where we think we have a key advantage here is through our IBM Spectrum storage product portfolio, specifically using automatic file management and then building GPFS file systems in the cloud, which support lots of different types of exports, NFS v3, v4, GPFS native protocol. One of the things that we've learned over time in working in the cloud is it's actually not as easy as somebody might think to build a performant file system in the cloud. Often people have to oversubscribe block storage to get I/O op entitlements. And what we're offering here is custom-built storage in the cloud where you're not paying for block storage and then building something on top of it. We're able to build these over our VPC bare metal. One of the other aspects of this too is once you set up the caches, you may have one-off cases where you've got to move a lot of data in and out of a cloud, in and out of your on-prem infrastructure. And one way that we offer to do this is to integrate Aspera, which is an IBM product, either into the LSF data manager or into as a standalone solution to move a lot of data in and out. The second component that's really important is job management. If you're thinking about leveraging hybrid cloud infrastructure or cloud-only infrastructure, you need to have a way to manage resources and cluster-based resources, either in the cloud or from on-prem to the cloud. And to solve that problem, we offer LSF, which is a world-class job management and resource management piece of infrastructure that you can create a remote cluster in the cloud. You can create cloud-only clusters. And if you have an on-prem installation of LSF, you can connect it in a multi-cluster fashion to your on-prem and make it as easy to submit a job in the cloud with the caching solutions as it is to submit to a different LSF queue. And that's what we really strive to do, because under pressure, design teams, foundry-facing teams who might be doing mask making are not going to want to learn something new in order to deliver something, particularly the closer you get to the delivery date. On top of all of this, or what we're building on top of it, is premier HPC virtual machines in the IBM cloud that can be auto-scaled and controlled by resource connectors through LSF. We are providing world-class security with our HyperProtect key services, financial cloud, and some other leading-edge security tools. And of course, we have multiple decades of HPC leadership and design leadership in designing our own tools and also building some of the world's most performant supercomputers. So just to summarize, to bring this together, what are the things that are EDA building blocks that we're pulling together? Secure EDA infrastructure in the cloud that leverages all the components I just talked about: security, LSF, spectrum storage, and AFM. We're building AI and HPC products in our cloud today. We've got multiple reference design flows, advanced technology nodes, accelerators. We also offer IBM Power VSIs in the cloud, if you're familiar with Power. Power is one of the key solutions that can actually get you a higher performance as a compute platform than you might get from x86-64 because of its advanced multi-threading technology. We have a growing ecosystem of partners, not only to help develop next-gen processes for different technology nodes. For example, we're working on beyond 2 nanometer today. We also have partnerships with Cadence, Synopsys, Siemens, Samsung, Rapidus, and also third-party IP agreements with some of the leading vendors. And finally, what we're also trying to do is democratize access to world-class EDA infrastructure in the cloud by offering lower barriers to access, i.e. making it easier for people to just configure a design environment, negotiate for licenses, and then hit the ground running. One of the other things that is also unique from an IBM perspective is we are still in the business of developing advanced device types, new processes, and we have an enormous partner ecosystem in our Albany, New York facility with New York Creates. So today in this facility, we're expanding to high-NA EUV. We have traditional EUV. We're expanding our line to fully explore different offerings for beyond 2 nanometer, and that's an active development today. The reason why this is important is we're still making new technology today. We're learning every day from not only the design, but also the process development that we're doing in Albany. And that helps us create infrastructure, answer questions, help people get to their design solutions much more quickly. So, just to summarize, how we're doing this, we're doing it not only alone, but with our ecosystem partners. We clearly can claim domain leadership in several areas that are critical to EDA and HPC. We believe we have a price performance point that's very competitive. We're able to enable hybrid cloud, secure collaboration, and make people successful in realizing design opportunities that they might not be able to realize if they were confined to their on-prem infrastructure. So what I'd like you to do now is to take you through some key examples of workflows that we've done and continue to do every day with our EDA as a solution cloud offering. I personally started my career in microelectronics 24 years ago. And I think if I've learned anything about this business and doing everything from process development through final design, is that A, there's never enough compute. Everybody's always looking for more compute as they get closer and closer to tape outs. And then there's 3 things that you absolutely have to do if you're going to do anything new in this business. The first thing you have to do is you have to design new content, which means you have to have infrastructure, tools, and capacity in order to do that. The second thing you have to do is take that design and transfer it to wafer through photolithography and etch processes. And a key component of that is OPC and mask making. And we'll talk a little bit about OPC, or optical proximity correction, in a second. And the third most important piece is to ensure that those designs are able to be transferred to wafer with particular litho and etch processes, wet processes. If you're designing outside or on the boundary of a particular design or PDK, you may not know where all the hotspots are. So you need to be able to actually print something or transfer something to mask that is transferable to wafer. If you can't do those 3 things, you can't do anything. All of them require significant compute capacity. So the first workload that I'm going to take you through is a cloudburst example for a power performance area flow using the Cadence Cerebrus technology. And what I'll do is walk you through what this actually does. This is really an AI-driven power performance area analysis tool. So you start with a typical RTL to GDS flow, and what you do is you run through once and generate what's called a baseline flow. Then you loop through the rest of the steps in the process: synthesis, floor planning, placement, clock tree synthesis, routing, and then eventually timing and closure. At each step, you're going to launch, and you can think about this in terms of a make file. I'm going to launch J trials at each step. And typically you want to start with 20, but you may end up with 40, 60, 80. And at each step, you're going to launch J synthesis runs with different parameters. Once those finish, you're going to pass parameters on to floor planning. You're going to do 20 concurrent floor planning runs. Then you're going to go on to placement and route, clock tree synthesis, routing, et cetera. And at each stage, you're going to launch J processes. And at the end of this, there's going to be an AI engine that's sitting on top of this that's going to analyze the parameters that were just generated, choose optimal parameters for the next set of runs, and then continue doing this loop until you either satisfy a cost function or you satisfy a certain number of iterations through the flow. Now, if you think about this from a very high level, if you have more than a handful of designers, combinatorically, if they all want to run at the same time, you're going to generate a lot of compute. It's very similar to verification. There's never enough compute for verification. In this case, this is an ideal case for hybrid cloud burst. Particularly if you have geographically separated teams, you want to be able to enable them to run wherever compute is available. So what we did in this flow is we set up a sample on-prem to hybrid cloud burst in the IBM cloud, where we created an on-prem proxy in Frankfurt, Germany, and we had compute in Sao Paulo. And what we did is configure this environment with all of the tools I talked about before, LSF, GPFS, AFM, or spectrum scale storage, and we had a centralized license server in Washington, DC. The exercise here was to see if we could forward a job from Frankfurt to Sao Paulo and have it run effectively. No stops, using input data that's in an automatic file management or AFM queue. Now with Cerebras, the only comparable runtime that you have is with the baseline flow. The rest of the trials themselves may vary in runtime because of parameter differences or because of where the engine is taking the flow. So what we're going to show you in a minute is the comparison between a job run in native GPFS and one that was forwarded from Frankfurt and run in a AFMQ or cache. Now, the picture on the right is really more to demonstrate the distance. Even if it was possible to have a wired distance like this, it's not actually true. It's got to go through a much longer path. But even with this path, we're talking about 6,000 miles. Okay, so there's a cache in Brazil. The job starts in Frankfurt. It gets forwarded via LSF. Job lands. It starts pulling data, and it runs. On the left-hand side here is a bar graph comparison. On the left-hand side is the job run in local GPFS. Each bar represents the runtime that each step took. And on the right-hand side is the forwarded job that's running in the AFMQ. So there was no input data in Sao Paulo. It all got pulled, started running. And what you can see from the bar graph, I don't expect anybody to read the numbers, runtimes are comparable. They're not the same. The AFM job is a little slower, but by and large, the runtimes are pretty manageable. You might accept that for the opportunity to get access to more compute. So what this demonstrates is an ability to run multi-geography, to go where the compute is, and have a solid and seamless data management strategy. The second case that I want to go over is a characterization bursting workload. This is done with the Cadence Liberate Trio suite. And what we're going to demonstrate is an LSF job that's forwarded, pulls data from an AFMQ again, runs in local GPFS, tars up the results, and pushes them back to a different queue. So in this diagram, we have the same kind of flow. We have an on-prem proxy in Frankfurt. This time, instead of running in Sao Paulo, we're running in Dallas. We have the same suite of products. We have AFM for caching and providing input data for the run. We have Spectrum storage. We have LSF configured in both places. And again, licensed servers in Washington, DC. So the idea here is a designer starts their run in Frankfurt. There's no compute there. There's compute in Dallas. We forward the job to Dallas. The job lands in Dallas, and it starts running. And as it starts running, it's pulling input data from the AFM cache. As it's doing that, what's going to happen in this particular job is there's going to be 7 control jobs. Each job is going to spawn an additional 100 characterization jobs across an LSF cluster. So a total of 707 jobs running concurrently until the end of the run. And what we have been able to demonstrate is if we run this job in local GPFS and compare it to jobs that were forwarded and using an input queue through AFM, that the runtimes are pretty comparable. They're not the same, but they're within an acceptable limit from our interpretations of what somebody would be willing to accept to have access to additional compute. And each one of these is looking at the 7 different control job steps and what the average runtime was to complete all 100 jobs. So you can see variation, clearly. But if you look at the averages, the average runtime for these jobs is pretty consistent. It's not clearly running in local GPFS with local input is going to give you the best results. But the variation is not as large as you might think from the distances that we're running this in. The next example that I'd like to go through with you is a foundry-facing example. This is the mask-making flow that we talked about, where you've got to take your design from a GDS or an OASIS layout format and transfer it to photolithography masks. So I'm just going to walk through very quickly what optical proximity correction is for those people who aren't familiar. Because unless you understand how it works, you probably don't understand the magnitude of what's happening. So right about the 90 nanometer node, which was about the time a little after I started, people started to realize that you couldn't just take a GDS file and apply a rules-based bias to it, put it on a photolithography mask, and have it print anywhere near target. So you can see in the upper flow there and cartoon that you might draw something and think you're going to get something close to the half an H there on the upper right-hand part of this diagram, but you're not. Or the long bar is going to come up with a lot of foreshortening. So about that time, people started thinking about how can I correct for the optical effects that are going on, and that's where optical proximity correction comes from. And you could think about optical proximity correction as a transform-based optimization process. What you're going to do is take in input, meaning design shapes that are on a particular layer. You're going to fragment them into vertices and edges, and then you're going to build two models. An optical model, which is the most physical thing. Think of a Fraunhofer diffraction model. And the second thing is a resist model that's an empirical model. And what you're doing in this process is you're first creating an aerial image, you're exposing it to the resist and taking a threshold from the resist model to determine what the current print or contour would look like in resist. You're then moving edges and adding vertices, and then and evaluating against a cost function, and then cycling through this process over and over again until you hit satisfy a cost function or hit a maximum number of iterations. So very simply, bring in the shapes, fragment them, create an aerial image and resist image, and start moving shapes. And once you hit a cost function target, you're going to store those data, and at the end, write them all out to disk. Now, from a computational perspective, this is not a shared memory parallel workload. This is true distributed memory. And it's, I get criticized for this, but think about it in terms of embarrassingly parallel. Our HPC guys say there's no such thing as embarrassingly parallel. So I put that caveat out there if you get criticized for saying it. But the idea here is we take an entire layout, we break it up into small segments or tiles. We then create a heap or a queue from those tiles. And then, as in the first part of a job, that process, when it's done with creating the heap or queue of tiles that it needs, will then spin up a number of remote processes and distribute each tile to one of the running worker processes and cycle through this process until all of the tiles have been processed. Typically, for a production level workload, we're talking about a job that's anywhere between 10,000 physical processes through 20,000 and 40,000 without GPUs. Today, people are starting to make the transition to GPUs, so think about this as a more traditional Linux cluster workload. So you can imagine that you need some significant compute capacity here. So what I'm about to show you are a couple of examples where we ran in cloud-only infrastructure. We did the transfer of data to the IBM cloud through a number of ways. But you could easily have done this with AFM or with Aspera. And all of the cluster work, the LSF jobs, were run in the cloud and run on IBM Cloud virtual machines. So what I'm showing you here is an example of a 2 nanometer RX scaling through 20,000 physical cores. Our objective here is to demonstrate linear scaling for the parts of the recipe that are meant to be linear scaling. The way that IBM writes our recipes, and other people write them differently, but we tend to combine a couple of different operations. So we'll do things like retargeting to prepare the data. We'll then do OPC, we'll do mask rule checks, and then write out the results. The I/O part of the recipe and some of the retargeting does not scale linearly. It has some dependencies on I/O. So what you see here when I'm breaking out OPC speedup versus total recipe speedup is you're seeing the different speedups based on which parts of the recipe we're running. So on the right-hand side with the total recipe, you're seeing some changes in slope as we go to higher and higher scaling, but by and large, linear. And if we're talking about OPC, we're scaling linearly up through 20,000 cores without too much process with the storage solutions and the job management and virtual machines that we just described. Another example is to take a 7 nanometer part from one of our server parts and run a thin wire and run it through the same flow. And this is a little different in the sense that it's covering a much larger area. This is a 585 millimeter squared layer where we split the retargeting and the data prep, or the first part of the prep between on-prem and the cloud, and then ran the job in the cloud. And through about 12,000 cores, we're also linearly scaling with this workload as well. So not only can we do research, macros, chiplets, test chips, but we can also do product pretty reliably. We also have been paying attention to future-facing workloads, people who may want to run cloud native. And we've been spending quite a bit of time on how can we enable multi-cloud Kubernetes flows, both on-prem and in a public cloud or multiple clouds. We, for example, for the Albany mask making that I told you about, we do most of our mask runs with Kubernetes. Either Red Hat OpenShift or what's called ROCs, Red Hat OpenShift Kubernetes service in the IBM cloud. And so what I'm going to show you are a couple of examples where we use Kubernetes instead of LSF. It's possible, and we're exploring this right now, that in the future you may be able to also use or manage LSF clusters under Kubernetes, so you don't have to make a choice necessarily. But if you're interested in doing cloud native flows, we're in the process of developing these flows and we're using them every day. The advantage here is you could put all of your tools, you could put all of your configurations in a container registry and only build a minimal storage infrastructure in a public cloud. And you could forward your jobs and run them with a managed Kubernetes service out of the box. So it increases flexibility. And if you turn on autoscalers, it also provides another method to control costs. So this is an example of a Kubernetes flow that we developed and presented at the 2022 Kubernetes Batch HPC Day. This is with one of our primary OPC tools using the Albany workloads. And again, we're showing speed up now with Kubernetes flows as opposed to straight LSF virtual machine scaling. And again, we're able to achieve linear scaling for through a little over 10,000 physical cores with the OPC part of the recipe. And with the total recipe, we do see some distances or differences in slope. We do need to work on these, but they're not catastrophic. These are things we think we can solve and bring things to a much tighter speed up and scaling overall. So in summary, what I hope I've been able to convince you of is that we have an offering that will enable you to seamlessly burst into the cloud or create your cloud-only infrastructure using LSF spectrum scale storage, and that you have a path to a cloud-native future. A critical element from our perspective is ease of use, making it easy for people to submit jobs and not having to learn new flows or special access to the cloud. We want to make sure that you can safely, securely forward your work to our public cloud offering and just make it as easy as submitting to a separate queue. Often we've found in talking to people and experienced ourselves that you've got to get the right data in the right place, and you don't want to pay other costs getting your data back out or the data you need. And that's one of the unique advantages of the IBM cloud. We can achieve linear scaling either with more traditional LSF workflows or Kubernetes-based flows, which I think positions us well for not only workloads today, but we give people or offer people a path to a cloud-native future. And also, I think if you think about it, if you go back to the premise that we made at the beginning of this part of the talk, if there's never enough compute, if you think about it, what you're doing is you're having to prioritize design projects that your company works on. One of the ways to get past that is to burst into a public cloud to enable the compute tools and resources. And this is an ideal way to do that overall. And with that, I'll take questions. Thank you very much, guys.
We have some microphones in the aisles if you'd like to ask a question.
So for on-prem, do we need IBM storage, or it can work with any storage?
No, actually, that's a very good question. We're able to create AFM caches from any NFS exportable mount. So if you, for example, have NetApp filers and you want to export a particular mount, we can create an AFM cache from that. Or if you have kernel-based NFS servers or custom servers, as long as they're NFS exportable, we can create a cache from it.
I'd just like to follow up on the response. So there are times when people have the data in object storage. So object storage could also be, quote unquote, the master data repository.
All right, I think that concludes our session. Thank you
right.
so much for joining us.
Thank you.
And we'll see you in Long Beach next year, 2026.